You know, in the world of AI, there's been this one single mantra for years: bigger is better. But what if that's just wrong? Today, we're diving into rStar-Math, a really fascinating development where small, super efficient AI models are learning to punch way, way above their weight class, especially when it comes to crazy complex math.
I mean, it sounds like something straight out of a sci-fi movie, right? Can a small, nimble AI really hold its own against the massive, resource-guzzling models that run the show? Well, that's the big question we're going to tackle. So to really get why this is such a huge deal, we've got to look at how things are right now. For years, the AI world has basically been in an arms race, and it's all been driven by one simple idea. For a while now, the thinking has been super simple. If you want a smarter AI, you build a bigger one. That means you feed it more data, you give it more parameters, which you can kind of think of as the AI's brain cells, and you just throw unbelievable amounts of computing power at it. It's really been an arms race where size is the only thing that matters. And you know these names, I'm sure. We're talking about the titans of the industry here. Models like GPT-4o, Claude 3.5, and that highly anticipated o1 from OpenAI. These are the Goliaths, built by companies with nearly unlimited resources, and they've totally set the bar for what a powerful AI is supposed to be. All right, so now let's bring in the David to our Goliath story, the small language model, or SLM. They're way faster, way more efficient, but they've always had this set of problems that have kept them out of the big leagues. SLMs are, well, exactly what they sound like. Instead of having trillions of those parameters like the giants, they're working in the billions. This makes them faster, cheaper to run, and honestly, a lot more accessible for everyone. The catch? Well, historically, they just haven't been as powerful. So the real question is, why haven't they been as powerful, especially with something like math? Well, the research points to a few big roadblocks. First, there just isn't enough high-quality math data to train them on. But even more important is this tricky problem. Sometimes a model gets the right final answer, but its logic to get there is totally flawed. It's basically hallucinating the steps. And how can you possibly teach an AI good reasoning if you can't even tell when its reasoning is bad? And this is exactly where rStar-Math comes in and flips the entire script. Instead of just trying to beat the giants at their own game of size, the researchers gave these small models a completely new playbook for how to think. To get there, the researchers kind of borrowed this concept from psychology you might have heard of: System 1 versus System 2 thinking. Most AI works like System 1. It's fast, it's intuitive, but it's also really prone to making mistakes. The goal here was to teach these small models how to use System 2 thinking, a much slower, more deliberate, and way deeper thought process. So instead of just, spitting out one single answer, the rStar-Math models use a technique called Monte Carlo Tree Search. The best way to picture it is like a chess computer that explores thousands of possible moves. The AI explores a whole bunch of different ways to solve the problem, step by step, figuring out which paths look the most promising. It's not about having one big, brilliant idea. It's about having lots of small, verified ones. Okay, but a new way of thinking? That also means you need a totally new way of learning. To get this right, the models basically had to go through a training montage and teach themselves how to get better. The researchers set up this really clever 4-round self-evolution process. It all starts in round 1 with a pretty decent base model. Then, in round 2, they train a second AI to act as a judge of good reasoning. They call it a process preference model, or PPM. Round 3 is where it gets cool. That new judge helps the main AI create even better training data for itself. And with each round, the models get smarter and smarter, letting them take on harder and harder problems. Now, this whole process is powered by 3 key innovations. Think of them as the secret sauce. First, the AI's reasoning steps are actually generated as Python code. That's huge, because it means you can run the code and check if it's correct automatically. No more bad logic sneaking past. Second is that smart judge, the PPM, that gets better and better at spotting good reasoning. And third is the self-evolution recipe itself, which creates this powerful feedback loop where the AI just keeps getting better. Okay, so we've got the strategy, we've seen the training, but did it actually work? Well, this is where the story gets really, really exciting. This is the moment of truth, right? After all this deep thinking, all this self-improvement, could a model with just a few billion parameters really go toe-to-toe with those trillion parameter titans? Just look at this. On a standard math benchmark test, the original 7 billion parameter model got a respectable 58.8%. Not bad. But after getting the rStar-Math treatment, its score rocketed up to an incredible 90%. That is not just an improvement, it's a total game changer.
And check out how transformative that is when you put it up against the giants. On that same math benchmark, a tiny 3.8 billion parameter model trained this way now scores an 86.4%, which beats both GPT-4o and OpenAI's new OLN1 preview. And the 7 billion parameter version? It ties the top-of-the-line OLN Mini at 90%. A small model didn't just compete. In some cases, it actually won.
And to put this into a real-world perspective that we can all appreciate, that 7 billion parameter model scored over 53% on the American Invitational Mathematics Examination. That's the Math Olympiad. A score like that would put it in the top 20% of the most brilliant high school math students in the entire country. We are way beyond just solving textbook problems now.
But honestly, the scores are just one part of the story. The truly mind-blowing part of this whole research is the unexpected new skills that started showing up because of this deep thinking process. And here is the real kicker. Even the researchers themselves seemed caught off guard by this. I'm going to quote directly from their paper here. "We unexpectedly observe that our deep thinking exhibits self-reflection. The model started doing something nobody explicitly trained them to do. They started catching their own mistakes."
Look at this example from the paper. The model starts trying to solve a problem down one complex path, but its own internal judge scores those steps as low quality, basically flagging an error. The model recognizes this. It effectively thinks, wait a second, this isn't working. It backtracks, tries a much simpler approach, and lands on the correct answer. This kind of self-correction has been like the holy grail in AI research for a long time.
So, when you really boil it all down, what this research shows us is a fundamental shift in AI. We're moving away from just building bigger models and toward building smarter ones. If a small AI can teach itself to reason, to self-correct, and to outperform the giants in a field as tough as mathematics, it just blows the doors wide open for what's possible. And it leaves us with one heck of a question. What's the next barrier it's going to learn to break?